All right, welcome back to day 2 of the calculus review in 2 days. This is integrals. So I think the vast majority of you have seen what this is, so we'll just get straight to it. Basic idea, if the derivative of a function, let's say the derivative of position is velocity, what do you call it if you want to go from velocity back to position? Antiderivative. Nicely done. All right, so what is the derivative of 2x plus 2? 2. What's the derivative of 2x plus 3? 2. What's the derivative of 2x plus 7?
2.
What's the derivative of 2x plus 52?
2.
What's the derivative of 2x plus 0? 2. Derivative of 2x minus 10?
2.
Okay, so the point is, if all these things have the same derivative, if I give you a function that, well, like 2x, what is its antiderivative? Well, you don't really know, right?
What?
You don't know. It's 2x plus something, or nothing. Yeah, some arbitrary constant, call that plus c. All right. So, fine. C is an arbitrary constant. What that means is, do you guys know what arbitrary means?
It's not like specified.
It's not specified. I like how you said that. And a constant is just some number, which we don't know. Okay. We call, for example, if your original function was at, then if you go backwards, you get 1/2 at squared plus c. That's called the indefinite integral, and it's written with a squiggle. Do you guys know why there is, that is the shape it is, that squiggle, that integral squiggle?
Isn't there like a Latin symbol?
A Latin symbol. It's interesting how you put that. Yes, it is a Latin symbol, but it's one that you're very familiar with. Why is it shaped like that? It's an S. Originally, this symbol right here was S. Why S? Sum. Oh. What's that mean?
It's a difference.
Yeah. The integral, yeah. Okay, we're going to get into that in a second. All right, back to this idea. Well, let's see. This is all pretty much review for you guys. If you have a function x, its derivative is velocity, right? What is the integral of velocity? Position plus a constant. Integral, right. And likewise with velocity and acceleration. If the derivative of velocity is acceleration, then the integral of acceleration is velocity plus c. All right, fine. Moving on. Here's a good example to do. Find the general equation for the position of an object under constant acceleration a. Okay, so what did I ask for? I asked for position, and what am I giving you? Acceleration. So what do you have to do to get position if you have acceleration? You have to integrate twice. Once for velocity, and then once again for position. Okay, fine, let's do it. Okay, so what's a good value for acceleration, by the way? A is a good value for acceleration. All right, so we're going to start with that. So integrate a of t, and you get at plus c1. Okay, go ahead, integrate that. What do you get?
At squared over 2.
1?
A over 2 t squared plus c1t plus c2.
Oh, okay, so 1/2 at squared plus c1t plus c2. That sounds great. You guys all know that equation, right? You've used that many times before in AP Physics B, right? Lots of experience with 1/2 AT squared plus C1t plus C2, right? Sounds very familiar. Everybody's nodding their head up and down and saying,
Sure.
what?
It's one of the kinematics equations.
Is it one of the kinematics equations?
1/2 AT squared is
Yeah, that one right there. Yeah, we've seen this one before. Yeah, right? Or have we? What's in there that we don't normally deal with? C1 and C2, right? Well, what is C1 and C2?
the initial velocity.
Oh. Okay. Can you prove it?
Yes.
All right, let's do it. Okay, so we expect the equation to look something like initial velocity times time plus 1/2 AT squared, right? Well, let's do it. Here we go. It should be this. Delta x equals VIT plus 1/2 AT squared. Well, what we have to do is we have to use our initial conditions to solve for C1 and solve for C2. So, let's solve for C1 first. Okay. What's a good initial velocity? No. I think VI is a good initial velocity. VI is a good initial. Let's use that for the initial velocity. So what if we say initial velocity, what does that really mean? What are we talking about? The velocity
at the start.
at time equals 0, right? So if we're going to write that out in math class, it would be V of 0 equals VI. Agree? And what that means is if we have an equation that's got V and T in it, we can plug in those values. And we do have an equation. Velocity equals AT plus C1. All right? Well, what's our velocity that we said before? VI. And what's our time? 0. So plug in VI for the velocity and plug in 0 for the time, and you get VI equals A times 0 plus C1. So what's C1? VI. All right. All right. So congratulations. We now know that the velocity equation is velocity equals acceleration times time plus VI. Oh, that should look familiar. Got it? Now, before we had C2 to take care of. How are we going to figure out what C2 is? In order to figure out one of these arbitrary constants, what do you need to know? You need to know some condition. Ah, that's right. We need to know initial position, right? So what is a good initial position? Xi. I like that. So, assuming the initial position is xi, that means x at time 0 is equal to xi, right? Well, now we can just take that and plug it straight in to the equation with x's in it. So, we knew that C1 was VI. So now we can go x equals 1/2 AT squared plus VIT plus C2. And of course we know that xi can be plugged in for x and 0 can be plugged in for time, and we get xi equals C2. Do all that, and we're left with this equation, which should look more or less familiar to you. What's wrong with it? It's closer, but it's still not quite the same.
There's two extra variables.
There's two x's. There's There's an x over here, and an x. What's the x on the right side? That's your initial x, and what's the x on the left side?
X at a time.
X right now. How do we make this equation match the equation that we actually like?
Subtract x item.
Subtract from both sides. And you're left with delta x equals VIT plus 1/2 AT squared. And that's the equation you used last year. Sound good? Yeah. Yeah, we're going to do several derivations. I try not to spend a whole lot of time deriving stuff in this course because the reality is you don't really learn a lot of physics when you're deriving stuff. But derivations are a part of the AP exam. So you will have to do certain ones. And this one you're not going to have to do because it's considered so easy that it's a waste of time. But later on, I think in the next couple days, you're going to see a couple derivations that you're going to do over and over and over again. All right, so here we go. Okay, so indefinite integrals always gives us a function whose derivative is the original function. Therefore, the indefinite integral is the inverse operation of a derivative. And that's all fine. Indefinite integral always gives you that plus c. How do you take care of a plus c? You have to know an initial condition. All right, you have to know or some condition. You could know the velocity at 5 seconds is equal to 2 meters per second, and that's good enough. But you have to know an extra bit of information to solve for the plus c. And by the way, for those of you who are inexperienced at this, solving for plus c is the step that beginners always forget to do. You always have to solve for plus c. All right, what's the meaning of an integral? You all know how to do it, but what is an integral?
The amount of area underneath the curve.
Okay, let's backtrack, and you're absolutely right about that. But integral's the opposite of a derivative, right? What was a derivative? A derivative is a slope. What's the opposite of taking the slope of something? And why? Okay, let's step back one further. How do you calculate a slope? Isn't slope fundamentally a process of dividing two numbers? So you're dividing something on the y-axis divided by something on the x-axis, right? You're dividing rise divided by run, right? What's the opposite of dividing? Multiplying. Rise times run. If you're multiplying rise times 1, what are you fundamentally doing? The area of a rectangle, right? Integrals are all about area, and that's why. Make sense? All right, so multiplying is the inverse of dividing. Area is inverse of the slope. Integrals are the inverse of derivatives. All right, let's go a little bit into that. Here it is all written out. Derivative is delta x over delta t. So an integral must be delta x equals v times delta t. All right. What that also means is, now let's take an example. Let's take this graph right here. You've got a velocity that's, what's true about this velocity right here? It's constant. Let's say it's 20 miles an hour for 2 hours. If you go 20 miles an hour for 2 hours, how far did you go? 40 miles. How did you figure that out?
Multiply the length of time by
The
velocity you're
20 miles an hour, which is this height right here, times the 2 hours, which is that width right there, and you get the area of that rectangle, which is 40 miles. And it even works out with the units too. Okay, fine. Sorry. Definite integral. Okay, sometimes it's convenient to solve an integral in a little bit different way. The different way is to, if we know an initial and a final condition, we can solve the integral and not ever have to deal with the plus c. A lot of times in the homework or in lecture, I'm going to do this instead. Basic idea is this. For example, problem. Assuming that the velocity as a function of time is given by the equation negative 9.8t, how far will an object fall between time equals 2 seconds and time equals 10 seconds? Okay, what did I just ask?
Distance traveled.
I asked for the displacement.
Yeah.
And what did I give you? I gave you velocity. So I gave you velocity. I'm asking for displacement. What are you going to have to do? The integral. Okay, good, because that'll give us. But I gave you 2 times. That's convenient. Here's how we write it. We start out by writing the basic integral, which is just delta x equals the integral of velocity dt. But since I gave you 2 times, what you can say is we actually write time 1 at the bottom, the initial time and the final time. And we call time 1 and time 2 the limits of integration. All right, everybody, real quick, what's the integral of negative 9.8t dt? This is 1/2, right? So negative 4.9t squared. Okay, so the next step. Sorry. 1/2 9.8t squared becomes negative 4.9t squared. And notice this little bar I put on the side with the 2 seconds and the 10 seconds. That's just reminding us that we are doing now a definite rather than an indefinite integral, and we don't have to write the plus c's anymore. All right. Next step. Delta x, which is the displacement, is negative 4.9t2 squared minus negative 4.9t1 squared. What's t1 and t2?
T1 is 2 seconds.
2 seconds and 10 seconds, right. So now all we have to do is plug in the 2 and the 10. We do all that, and we end up with an actual number. Got it? Why does this work? Why did we end up having to subtract something from something else? What is this something right here? Negative 4.9t2 squared. What is that? Physically, what does it represent?
That's the position at. That's the position at t plus 10.
That is the position when you're at 10 seconds. What's this one right here? Position at 2 seconds. So what are you doing? You've the position at 10 seconds minus the position at 2 seconds should give you the distance or the displacement between those two positions. Does that make sense? That's why this works. You're taking something that would normally be a whole bunch of steps, or as an indefinite integral, you'd have to plug in that condition, solve for c, plug it all in, come up with an answer for the position at 2 seconds. Then do that all over again, come up with an answer for the position at 10 seconds, then subtract the 2. This does it all in one step. Make sense? All right, so there are times when it's just quicker to do a definite rather than an indefinite integral. You can do it either way. You could have solved this problem with an indefinite integral, but it's just quicker in this case. All right. Last one, and this little piece is kind of cool. Yeah, it's not something that's going to show up on the AP test, but it is a good thing for you to understand about the way integrals work. It's called Riemann Sums. Raise your hand if you've done Riemann Sums already. Okay. All right, here we go. Yeah, I said before, I briefly explained that integration gives you area under the curve, but we're really going to go into why. Okay, let's say I gave you a function, t squared plus 1. What shape is it?
Parabola.
It's a parabola. Smiley or frowny?
Smiley.
Smiley, right? Because it's a positive parabola. It's a positive. It's a smiley one. Okay. And then I said, well, I want to know the area from here to here under this parabola. How would you do it?
Lots of rectangles.
Yeah, you could count rectangles. And that would work, right? Let's say, let's see, from here to here was 1. And from here to here was, I don't know, 2. What would the, if you counted up the area of this rectangle and that rectangle, what would you get for an area? Can you guys do that in your head?
3.
Okay, so this height is 1 and this width is 1, so what's the area of this one?
1.
And this height is 2 and this width is 1, so what's this area?
2.
So what's the total area?
3.
Is that an overestimate or an underestimate?
Underestimate.
Okay, why?
You're missing some area.
Okay, so how do you deal with that? Smaller rectangles. Okay, so if you do, well, what about this? What about this? If say you're too lazy to do smaller rectangles, what if instead of going from this width and this height, I did this width and this height for an area like that? What would that one be? That would be 2, right? And what if I did this width and this height, and say that was 4? So 2 plus 4 is 6. So I would know that my answer is somewhere between what and what? 3 and 6. All right. But like an astute student once said, if you do smaller rectangles, you can get a more accurate area estimate, right? Is there a way to do this kind of in one step? Or are there other better ways to do this other than slicing it up a whole bunch of times?
Take the rectangle from the middle.
The rectangle from the middle.
Instead of taking 1 or 2 and like the left or the right endpoints, you see where it crosses at the middle of the curve. So you use that as your height.
Oh, you're saying the average of the overestimate and the underestimate.
Yeah.
Ah. So what you're effectively doing is turning this into a triangle and this into a triangle. So you're taking this box, that triangle, and that triangle. I like it. All right, and that does work. All right, but of course the ultimate solution is just brute force the thing. Slice it into a whole bunch of boxes, and then you get a really good answer. All right, so we're going to do that. So it turns out if you do it, I did it. 10 slices. It comes out to be 4.28 meters. 4 slices up here is 3.75. 20 slices, 4.47. 40 slices, 4.57. 200 slices, 4.65. 2,000 slices, 4.66. What do you think 10,000 slices will give you? 666, right? A million slices, 4.66666. Makes sense? So what's it approaching?
1.67. 4 and 2 thirds.
Actually, yeah, it's approaching 4 2/3. Guess what you get when you integrate it? All right. Oh, by the way, why did I bother slicing it up a bajillion times? What's the point? Does anyone ever do this? A computer does. Computers are really, really good at making a lot of calculations really, really rapidly. Turns out that a lot of what the computers are designed to do is slice up things like this into a million or a billion pieces. and then do all the calculations really, really fast. I did this in Excel. But anytime you ask a computer to integrate, what's it going to do?
Just slice it up into a whole bunch of
Yeah, and perform all those calculations as fast as it can. And it might perform 1 billion calculations per second. So, yeah, they can do this real fast. All right? So, 1 billion calculations, well, it's actually not going to be 1 billion in 1 second, but it might take 10 seconds. Make sense? All right, cool. And the more slices, the more accurate it is. So does a computer typically give an exact answer? What? Not always. Is there ever a case where a computer will give you an exact answer to an integral? How? When the integral is 1 or 0. So something trivial. Okay, I agree. When else?
When the curve is constant.
When the curve is constant, yes. When it's a straight line, in other words, right?
Yeah.
Okay, when else? When you're using Wolfram alpha. Or Maple, or Mathematica.
Oh, like a specific program.
Right, that's built to give you an exact answer. All right, usually what computers are really good at giving you approximations that are very, very precise. And usually what will happen is the computer has a certain bit buffer, and once it's filled its bit buffer with so many decimal points of precision, it's like, there's your answer to 64 digits, or whatever it happens to be, right? Or usually on your calculator, I think it's like 16 digits. And when it's within that 16 digits, it calls it good, which is why a lot of times your calculator will report an answer of 1 instead of an answer of 0.99999999999, right? If you were to say divide 9 by 9, internally it knows that after a certain amount, it's just going to round it to 1. Sound good? Did that just go over your head? No. Yes? All right. All right. Computers don't give exact answers. They give approximations. Really, really good approximations when they're doing calculations. Yeah?
So, like, all those programs that you said that give you an exact answer, what would they do if the answer was irrational?
If the answer is irrational, so it's got to have some lookup table to know that, say your answer is in terms of E, right? And you're looking for an answer of 2E. It's going to carry out that calculation and know after a certain number of digits that if it matches what 2E would be, it's going to report 2E. And if it doesn't match, it's going to report, 5.5, et cetera, et cetera, et cetera, et cetera, whatever the decimal approximation of 2E is. Make sense? All right. Okay, so all that being said, that's, again, way beyond the scope of this course, but kind of cool. All right, so back to that idea of the integral symbol being an S, right? Okay, well, okay, here we go. We know that the area under this curve, right here, is the sum of all of these individual areas. That rectangle, that rectangle, that rectangle, and that rectangle, right? And we can get it more and more precise if we make the rectangles smaller and smaller slices because these areas of these little goofy little shapes above get smaller and smaller. Okay, fine. Here's the cool part. The total area of all the rectangles is given by the sum of the height, or the VI, times the width, which is delta t. Agree? The total area is equal to the Greek letter sigma sum VI times delta t. Approximately. What's the difference between this equation and this equation.
Integrals have more exact answers.
They say almost exactly the same thing. Delta x is delta x, agree? Equal sign is equal sign, except, well, that one's not really an equal sign. V is V. T is T. What's delta mean again? Change. What's the difference between this delta and that little d? What's the difference? Are they the same or different?
Isn't it nominal? Like, it's just the way that it's written that's different. But like
But dt is infinitely small, whereas delta t could be any value, depending on
Yes.
how accurate.
You got it. dt is just delta t taken to the extremely small. Does that make sense? And this is a very important word that you need to know. The word is called a differential. A differential is an extremely small delta. All right? We say it's infinitesimally small. So differential t versus delta t. The v's are the same. Differential is an extremely small delta. In a few days, we're going to talk about something called differential equations. What is a differential equation? An equation with a differential in it. So I suppose, by definition, this is a differential equation. Though it's a kind of a trivial one, but it is. All right, and we're going to spend a lot of time playing around in differential equations in this course. You guys know differential equations is usually the class you take right after you take multivariable calculus? Okay, good. You're going to love it. Differential equations is awesome. Explains everything. Okay, back, I digress. What's the difference between this and this? This letter. What letter is this?
Sigma.
Sigma. What letter is this? Big S. What's the difference? Or are they the same thing? One's curvy and one's jaggy. What's the difference between that letter and that symbol? What's this one tell you to do? What's that mean?
Add everything.
Add up all the pieces. What's this letter mean? Add up all the pieces. Why do we use a different letter? One, you're adding up an infinite number of infinitesimal pieces. This one, you're adding a finite number of pieces of finite size. Does that make sense? These two equations are almost identical. And that's the difference. So every time you think you see an integral sign, and to you, for the novice, it appears just, oh, that just means I do an integral, right? I take whatever's inside there and integrate it. Well, what you're really doing is you're adding up a bunch of pieces of dt, of width dt, and height v. Sound good? All right, that's integration in a nutshell. Any questions? All right. Okay. So now that we've had all that practice, integrate t squared plus 1 from 0 to 2. Go. What do you get? T cubed divided by 3 plus t plus c. But I said from 0 to 2. So what kind of integral should you do?
What was that again?
Doing it in your head? Oh yeah.
14 thirds.
14 thirds? Alright, here's what it looks like. Plug it all in, 14 thirds, comes out to be 4.6 4.6666666 or 4.67. Sound good? All right. So lecture notes are online, and that's it.